Okay, so today we kind of switch topic in the sense that we are trying to touch upon neutrino-related subjects, of course, in connection with muon beams and possible reuses of these beams or uses of the beams. So later we will have a more neutrino physics dedicated talk by Luca. And before that, now we start with Chris, who's gonna tell us paths to a muon collider.
Thank you. So we've had, in the last days, many quite fascinating presentations about physics beyond the standard model, ways of intercepting neutrino beams that are created by the decay of the muon beams in a muon collider. And I thought we'd do something a little different today, which is to precipitate a discussion Ah, no. Precipitate a discussion about a topic that we haven't addressed so far in this workshop that I think needs to be addressed. So I begin with a story. I spent a lot of time at CERN, and several years ago, I was on one of my extended visits at CERN, and one of my neighbors in the edge of building 53 and 4 was Luciano Maiani, former director general of CERN. And whenever Luciano didn't want to do any work, he would come to my office and bother me, and we'd talk about non-standard hadrons and things like that. One day he came bursting through the door of my office and he said, "Chris, I've been thinking you should have built the SSC. It was the perfect machine." So this was not a revelation to me, of course. I offered to show him my stigmata. And today I wear the only surviving feature of the SSC, which is a wonderful t-shirt. So this is a slightly cautionary tale to say that even if you have a wonderful idea, and you can convince a former director general of CERN that your idea was the perfect idea, it's not so easy. And so in order to make these things happen, you need a good technical foundation. You need to form alliances with people. Not all of your allies will have interests that are identical to yours, but they have to be close enough. And that will be part of the slightly technical discussion that I'll get to later. Now, some of you, Luciana, Fabiola is not yet former. She's on shell. She will always be on shell. So many people know that we're very good friends, and I always have to say, I do not speak for the Director General of CERN, which is true, except for Luciano in this one instance. Now, many of you were not yet born in 1993, or some of you are maybe not yet born. Well, you look very young. So I remind you what this perfect machine was. This was to be a 20 plus 20 TeV proton-proton collider. Luminosity was 10 to the 33 per square centimeter per second. It could go up a little higher. That modest luminosity was enabled by the fact that if you wanted to explore the 1 TeV scale and you had this excessive energy of 40 TeV in the center of mass, you didn't need to push the detector requirements. At the time that this was being conceived in the middle 1980s, we were frightened about building detectors that would sustain even above 10 to the 32 or 10 to the 33 per square centimeter per second. It had a circumference which some of you will find familiar today from the discussion of the FCC, EE, and NHH, 87 kilometers around. The dipoles at the time were 6.6 Teslas. That was a 50% improvement on the Tevatron dipoles, but far from what we can imagine doing today when the LHC is run at over 8 Teslas in the dipoles. You see here the location of the laboratory south of Dallas in Texas. Approximately 1/3 of the ring was excavated, the tunnel was built before the United States Congress, in its wisdom, terminated the project. So you can get very far along the way and still not have anything to show for it, except, of course, all the work that was done in preparing the design of the detectors, many of which found their way into the Atlas and CMS detectors at CERN. So that's just to say it's not easy, and you have to work very hard to make these things happen. I remind you of a couple of papers from the beginning of time when we started to think about the notion of a neutrino factory in the modern sense. This is a bit after Dave Neuffer had made his sketch. There was a meeting at Fermilab in 1997, optimistically titled The Physics of the First Muon Collider and the Front End of a Muon Collider. So I gave a summary talk there, which is called Physics with a Millimole of Muons. It will have a certain antique charm if you look at it because we knew so little, and yet we were so optimistic we thought of all the things that might happen. And one of the things that I emphasize in the final paragraphs was something that is a statement that's always true. We can write down or think about all the wonderful things that we could do with a new machine. And it is natural to suppose, let's imagine that we have this machine today. Think of all the wonderful things it will do that nothing else can do. But if it takes decades to realize the new machine, you have to try to have some perspective about what it will add to knowledge at the time it actually happens, and sort of have some respect for what other people are doing without being frightened away totally. There's also an introductory talk to the first neutrino factory meeting in 1999, in which I outlined what were then the leading questions in neutrino physics. This was at a time before we had confirmation that neutrinos oscillate, and so again, it will be valuable for its antique charm, as well as for the highly perceptive comments you might find there. Okay, so I start by summarizing some outstanding questions about neutrino physics. This is actually taken from a much longer talk in which I started compiling before the snowmass process in the United States all the things I didn't know, semi-infinite list. And part of the reason for motivation for that was to encourage my colleagues to think broadly, not simply about one or two big questions, but to think about many things. And I think at last count, my number of questions is 120, or a little over 120, in many topics having to do with particle physics. So if I were a better person, I would write this down with a narrative, and maybe that will happen in the next months. So for the question of neutrino physics, I think there are two elements. One is the properties of neutrinos, things that we'd like to know about them. That's what this concerns with. Another question that we'll get to is neutrinos as instruments to learn other things about the physics that that's outstanding. So these are questions you could easily make. How is neutrino mass a sign of physics beyond the standard model? I have to say I have mixed feelings about this, because if history had been different, if we had discovered neutrino oscillations at an earlier moment, we would have built right-handed neutrinos into what we call a standard model. It is nevertheless true that in the order in which we learn things, that came later. And so we have to add by hand, we think, right-handed neutrinos, and therefore it's manifestly some element of physics beyond on the standard model. My neutrino friends are always happy to say that neutrino mass is the first sign of physics beyond the standard model. And because I have a different point of view, I would like to say that it is a sign of physics beyond the standard model, but the first sign of physics beyond the standard model is the electron mass. Because within the standard model, there is no calculation that we could even imagine doing that will tell us the value of the neutrino mass. Of course, spontaneous symmetry breaking, as outlined by Weinberg, gives us the possibility of a Yukawa coupling that leads to the value of the electron mass and all the other things. But that is mysterious to us all. And as you know, for decades, people have tried to make different stories that might account for at least the relationship between lepton and quark masses, with little success until now. Second is a more specific and technical question. What's the order of levels? We know about the mass squared differences. We don't know whether the solar pair lies below or above the other one. We don't know the absolute scale of neutrino masses. Katrin has been making great progress, closing in on a goal of about 0.2 of an electron volt for the neutrino that is associated with beta decay. Cosmological bounds, which depend on certain technical assumptions, are coming down and down. I have a fantasy that at some point there will be a direct detection from Katrin, and there will be a cosmological bound that is a smaller number, leading us to conclude that there's something we don't understand about the thermal history of the universe. That would be a wonderful stimulus to thought, but we'll see how the rulers of the universe rule on that. What's the flavor composition of nu3? Is it richer in nu mu or nu tau? That's the octant question sometimes posed. Is CP violated in neutrino oscillations, and to what degree? Are neutrinos Majorana particles? Important for thinking about the possibility of leptogenesis and other things. Is it enough to have 3 light left-handed neutrinos, or do we have to invent more things? Depending on which unconfirmed data set you take seriously, there may be evidence for 1 or 2 or n sterile neutrinos. It's an open possibility. Where would those come from? If there are right-handed neutrinos which seem implicated by the notion of neutrino mass, what is their nature? Are there light sterile neutrinos? How would they arise? You know, the natural way to get sterile neutrinos was in the seesaw mechanism to say that they live way up in the sky. If they're contributing to oscillations that we see now, they don't live way up in the sky. So where do they come from? How does it fit in? Do they have non-standard interactions beyond those mediated by W plus minus and Z? So one question, because experiment other than from reactors and beta decay has not given us copious sources of electron neutrinos. We don't know a lot directly about their interactions or, for example, the oscillations. One thing that would be nice to know is the nature of electron neutrino to tau neutrino oscillations. This is something for which we don't have direct access at the moment. Do they contribute? Are they all stable? That's something that we can see, we can try to look at by observing the flavor content of neutrinos that land here from the great beyond. You can get combinations of the flavors that would not happen if in a normal world. Do they contribute appreciably to the dark matter of the universe? The theorists have gone everywhere on this question. Once upon a time, they were all of the dark matter, then they're none of the dark matter. Now they may be a little bit. That's an important thing. And will they give us insight into the matter axis in the universe through leptogenesis? That is a dream, although an indirect dream, of the possibility of detecting CP violation in the neutrino sector. Okay. Now, our forthcoming neutrino experiments, Dune and Hyper-K, have aspirations beyond the question of neutrino oscillations. And I give you here with links that you can click some of the recent documents from my Dune friends on what they hope to do for physics beyond the standard model searches. It's a long list of things that look as if they're achievable. One of the things to keep in mind, and this is in the spirit of not being frightened by what other people can do, but being aware of it. We heard a lot of talk yesterday about the possibility of using the beam dumps that accompany muon colliders or the sources of muons for them. There will also be beam dumps for the super beams that will drive Hyper-K and Dune. And there's been at least a little bit of thinking about, inspired by the kind of things that we heard yesterday and the day before, inspired by those things, what you might do with the beam dumps on site at Fermilab or at JPark in order to do at a restricted energies. In the case of the Fermilab beam line, the useful energies of the muons would be between about 15 and 50 GeV, so not the TeV scale that we've heard about in the last couple of days. But it's important to be aware of the things that might be done in the next decade or two as we're moving toward the question of a muon collider. People at Fermilab have been talking about improving the infrastructure of the accelerators. Many elements in the accelerator chain are 50 years old or more. Same is true at CERN, of course, but both of them have been, to one degree or another, improved over time. So there was a little workshop in which you'll see a lot of the ideas that we've discussed here and some others as a possible motivation for specific improvements in the Fermilab accelerator complex and so on. Okay, now you all know, because we've been talking about it in the last days, that the bug of muons, which is that they decay, can be turned into a feature, or at least can be hoped to be a feature, because we know how to describe the spectrum of neutrinos that comes from muon decay. And here are two sketches of the density, the concentration of muon antineutrinos from mu plus decay and electron neutrinos from mu plus decay. And these will be the sources of beams. So one possibility, and years ago when we first started thinking about these things, the notion was it would be very, very hard to make beams bright enough to collide with appreciable luminosity. I remember the accelerator physicists at Fermilab coming to me and saying, well, if we gave you 10 to the 29, could you do something smart with it? Well, you can always do something, but it restricts your aspirations at that level. Well, people have gotten more serious and done more work. Nevertheless, it was thought that a first step to show that you could capture muons, you could confine them, you could accelerate them, would be to make a single beam neutrino factory. And the idea there is that you do all the miracles that you need to do. You inject finally into a racetrack at some high energy. You pick the energy to be big enough to do tau neutrino appearance or small enough to not do that, and off you go. So one of the things that's been looked at periodically over time, and most recently Peter Denton and Julia Gerlein did another nice look at this, is what would you do in the dune setting if you could illuminate dune not only with the super beams from Fermilab that we imagine, but with some sort of neutrino factory beams because of a different mixture here. And so here's a nice paper. I think it was finally updated in March in spite of that 24 date. That's worth looking at to see a fairly comprehensive view of what you might be able to do. Now, the other thing that I think bears discussion, and I hope to get either your instantaneous remarks or your thoughtful consideration, is what can you do beyond the oscillation physics for which the original dream of a neutrino factory was conceived. And the thing to keep in mind is that the density of neutrinos is very high. So you can imagine on campus having 10 to the 20, 10 to the 21 neutrinos per year going through your detector. At that level, you do not necessarily need a battleship's worth of material in order to see interactions. In fact, you can fantasize about having thin targets, polarized targets, maybe even active targets, depending on the energy at which you make the neutrinos. And so there's a lot of physics that in principle could be done there. I think it doesn't take much thinking to understand that the possibilities are amazing. The real question is, are the possibilities interesting? Can you do physics that you really need to do in a way that you couldn't do otherwise? So one of the things to keep in mind is that there has been in the United States at JLab, an electron lab, which has done experiments with 6 and 12, and now they hope 24 GeV electron beams, and at various other sites around the world. There's been an extensive program of studying nucleon structure to try to understand what's the strange quark content, how are spins distributed, and so on, doing things that are too complicated for me, like generalized parton distributions, three-dimensional parton distributions, and so on. Some of that will be continued at the electron-ion collider when it should happen. Others, they've sort of run their course. And so the question is, could you, using neutrino beams, repeat that program and extend it by the fact that neutrinos feel other flavors than the electric charge, which is felt by the electrons? So there have been some looks at that. There's a paper 25 years ago by Richard Ball and two neutrino physicists, Debbie Harris and Kevin McFarland, on trying to decompose the flavor structure of the nucleon using neutrinos at a neutrino factory. And then a couple of recent papers on generalities of the physics case for a neutrino factory and specific electroweak observables in the neutrino electron scattering by Andre and Adrian. So I think the first question for all of us to think about, at least a little bit, is, could you do these experiments? Would they be interesting? Would they really add to knowledge? And then from the point of view of promoting a community that would support the notion of a muon collider, would these bring new people into the fold? At Fermilab, because I've known it over many years, and because recently we had terrible difficulty after COVID getting anybody to the laboratory, it's plain to me that our biggest need as a laboratory is to have more smart people coming through the gate every day. And so if we can find ways to attract more smart people, maybe from a community that's adjacent to ours, but not central to it, that would be a good thing. So my question for you, for which we don't have to have an instant answer, is how aligned is a neutrino factory with a 10 TeV collider, either technically in terms of building community support? The first response people have is all over the map, from it's not on a straight line to the muon collider, I don't want to hear about it, to it's at least got a vector which is partly in the direction I want to go, maybe it would be a good thing, and so on. And I think it is worth spending some quality thinking time to discuss these things and to understand what the technical requirements would be. Would it be a way of getting there faster? Is it a way of having a demonstration that you can do physics early on, and so on? I would say one last thing, that depending on how the muons are accelerated in preparation for injection into a collider ring for muons, you may have a series of recirculating linear accelerators. And every time you have a straight section or a straight accelerating cave, that is a place in which there's going to be a flux of neutrinos. Are those too tiny to worry about? Could you imagine stage by stage doing some neutrino experiments that would be of interest, not just as stunts, but from which we could learn things, and so on? So that's what I had to say, and I'd love to hear your response and comments.
Oh, okay. Absolutely.
Please.
Thank you very much, Chris. Very nice to hear. Okay, clearly my personal opinion is that to your question, it is an essential step. I would like also to reinforce that with my presentation. But I have a question on the previous slide. You talk about well-characterized beams, neutrino beams. And can you express more detail more what you mean by well characterized? Because this is a key feature for the neutrino.
It is a key feature. So As a spectator, I was marked by the experience of mini boon, which did not characterize its beam very well at first. And the collaborators on mini boon after the fact spent infinite effort, brilliant work to try to pin down what was in their beam at the beginning. So I never want anybody to do that again. On Dune, you know, I'm a spectator, not a participant. Because of my how shall I say, my experience from a distance with mini boon, I would have thought Dune should have a really first class near detector from the beginning. Your collaboration has taken a different point of view, which has a certain logic to it, which is there's only going to be one more supernova in my lifetime. And so if I waste time building a near detector and haven't finished my far detector, I will miss out and I need to live another 100 years. Well, that's partly, it's certainly a physics motivated choice, but I would be happier in a world with infinite funds and human resources. I would be happier from the beginning to have really good near detectors. I know they're supposed to come in time, but okay. Now, in this case, we can at least calculate, and I hope then validate what the content of the beams is. So that's part of the hope for the neutrino factory.
But do you think it's really just a person power limitation on this particular issue, having near detectors as a high priority?
Oh, it's money as much as anything, right? I mean, you know, if you do something on a blackboard, you don't have to worry about these things. But these people actually have to make it.
I'm aware of this difference, yes. Okay.
So two quick questions. One, non-physics. Is that Super Collider t-shirt original?
It is original, yes.
And the second,
I have a total of 3 40-year-olds t-shirts, 2 from running the Beta Breakers race in San Francisco,
and that,
which I can wear with pride because nobody knows what they are. And now I think nobody knows what this is.
and the second physics question. Do you know of anyone that's thought about using the RLA as a neutrino source? I mean, I think it's interesting, and I was just looking at rough numbers, but I guess both the IMCC and the Fermilab folks, no one's actually done any studies on the RLA so far. And just the rough parameters, I'm seeing like the first RLA of going from 1 to 5 GeV, and then you have 4.5 passes, and then another one going 5 to 63 GeV, 4.5 passes. But it also gives you a nice energy spread too. Like if you want to have your neutrino beam because each pass and you have a time structure.
It could, and the degree to which you can use timing to know something about what you think is coming at you is a question that certainly can be answered. Just 2 weeks ago, my colleagues, Patty Fox and Pedro Machado, were commissioned by our interim director to think about this.
Oh, okay, great.
So I know that they've done some little calculation. Maybe they'll be serious about it. It's kind of interesting to see what the fluxes would be, whether early on in building a chain, you could do some experiments of that kind. But I don't think we know an answer yet.
Okay, thanks.
Anyone wants to comment more?
I think the way you posed the question on the last slide of, you know, is this a distraction or an essential step? I think that saying that it's a step is the thing that I take issue with, because as I see it, anything that's neutrino should be parallel, right? You don't want, it's only a distraction if it slows down the the project of getting to a high energy muon collider. And I don't think there's any reason that it should. So I think that, you know, as we talk about how this is done, it's important to always be talking about how it can advance along with it, improve the physics case of the things that you want to do and get them, make them have a better case, and not as something that is a step in between things that you would otherwise do for a muon collider.
Mhm.
Yeah.
Very good.
Should we reason as this were the heavy ions of the LHC or something like that? 3 months a year, you do that?
I mean, it's not a different beam, right? And necessary. So we're talking about what you can do along the literal beam that you would be using for a muon collider. We're not talking about doing a special run to hit a particular energy. We're talking about get your energy you want from some stage along a muon collider. You know, I mean, I'm not saying no one should ever think about that. If you want to think about some beam that we would never want for a muon collider, you know, make a case if you want to. But I think that most of the interest from the community is going to be from stuff that's not a separate run in any way, right?
I think it will depend on the evolution of cooling technology.
Yeah.
You know, did you get to a point where you've cooled enough that you could plausibly make a neutrino factory,
Mm-hmm.
and you need time to think or make improvements or do something else? It could be pushing the program without waiting for the final perfection of the cooling. But as with everything in physics, the numbers matter.
Yeah.
Right.
Yeah.
But I think Roberto's point is that that analogy is right, which is to say, engage another community to make the thing happen faster,
Right.
not
Right.
slower.
Exactly.
Exactly. So in that way.
Still, there might be some month of the year where you push high quality neutrinos, let's say, for some reason, and I don't know. I just use blackboards. Sorry.
I mean, I have a factory that simulates.
Hmm.
Yeah.
But yeah, I think we can.
Okay. So ideally, everybody happy at the same time.
So I think there is the opportunity that we don't need to dedicate our beam time to the neutrino physics. As we know, muon decays all the time, right? We actually have a high intensity muon beam at every stage. It is a constant source of neutrinos. That's why every strict session is actually an enhanced neutrino production point. So just maybe while we are just running our or plan to run accelerating our muons, there are some natural for us to put some neutrino detectors. As I did in my paper, I will talk next week about the muon collider do have a lot of neutrino events within its major detector already, but I think the discussion of every acceleration stages, maybe you all have additional neutrino opportunities. It might be a very interesting practice to work at. In particular, as different stages have different energy, as some of you mentioned already. And if I can use a timing information, so I can actually sample different neutrino energies with its properties. So maybe it's a add-on experiment without us losing any. That evaluation has to be done.
Well, so I guess the other question, I mean, like you start with all the various questions about neutrino physics. If the real goal of a neutrino factory is just to beat down the systematics that come out of T to hyper K and Dune, then you might need a very different kind of number in terms of neutrinos than if you're trying to do neutrino factory to like really get the angle down to like one more decimal place or something like that. So, I mean, like, yeah, I mean, thinking about the RLA, like if you didn't want to build a separate muon storage ring and you just needed some fraction of high quality things, if you just aim RLA2 towards Dune or towards some neutrino detector, that might be a much cheaper and faster way to beat down the systematics. But if you're not caring about the next decimal place for your mixing angle or something.
Yeah, I think the one needs thought beyond just writing down vague things. about the promise for long baseline and for on-campus experiments and what those would be.
I mean, I think the question of special runs is very interesting. I mean, is there a world in which we say the neutrino, like some part of the neutrino program doesn't need as cool of a beam, but does want the number up? Can we pull a beam out, and does want the energy high, for example? Can we pull the beam out before sending it through the lossy cooling process and shove it into the acceleration process successfully? Is there any way of playing with that trade-off, you know, where we retain an extra order of magnitude of neutrinos at high energy where we don't need it so cool?
For some of these questions, probably for all of the questions, you actually have to design an experiment and understand the numbers and what it would take. But the opportunity to have both mu pluses and mu minuses could be useful. As I say, there are things like electron to tau oscillations that I don't see how to get otherwise. That requires a certain energy before you get to see the taus and a certain distance. So that's not an on-campus experiment. And to really go through what would be the possibilities. And as I say, get beyond the gee whiz stage and say, do I really want to do these things?
Yeah.
Would I, as an experimenter, I can say this easily, spend 15 years of my life making this happen or not?
Exactly.
That's a test.
To the very least, I think we need to have more discussions with people that know what are the neutrino physics problems. And then you can start asking which experiment I want to design, what I want to measure, what kind of beams I need. And yeah, we have been trying this week to gather a little bit of this, but I think we can do better. And everyone singly, you know, each of us can go and establish more relations. I don't know. In fact, you talked about communities, and that's probably one of the problems that they're
Yes.
plural.
That's right.
We are a bit separated in a
There
sense.
is,
And
there is very little crosstalk. And I think it will depend in different countries on the funding arrangements. So in the US, nuclear and particle physics have been separated for 30 years or so. I'm told they may be coming back together, whether that's just an evil plot by the nuclear physicists to steal our money, or whether it will foster more intellectual commerce remains to be seen, but it's something we should try to take advantage of.
Is the demonstrator program too low intensity to get interesting neutrinos out of that, or is there a possibility there?
Well, I think that's a perfect question. As we heard from Dave yesterday, even he doesn't know what the demonstrator is yet. And so that's going to be evolving. And the notion that the specifics of that might be coupled to some short-term physics program deserve discussion. Yeah.
Oh, yeah, it's definitely a real yeah, that's definitely a real possibility. And yeah, you could really design it to be to be a significant fraction of a neutrino factory, say, or
Yeah.
something could, yeah, you could, something like the new storm scale thing you could easily do. Or, well, not easily means less than billions, but
Yeah.
yeah, definitely.
Someone has to care and make it happen.
So maybe re-asking Larry's question to Dave. So new storm, you're not thinking about accelerated, but how much do you have to cool the beam to get into like an order 300 megahertz or 700 megahertz RF? And like if you don't want to build all the way through final cooling, how much cooling do you really need? How many orders of magnitude to accelerate it?
You know, you have to calculate that, and sort of probably 700 megahertz is kind of small, but the 325 or that scale, you really only need to cool by, well, actually even wouldn't even really need to have to cool, but just sort of reduce the phase space or acceptance factor of 10, and yeah, and you would be there. And which you can either do by collimation or initial cooling stage. Yeah. So yeah, definitely there's, but yeah, one has to design in detail, but yeah, this definitely could be done.
So thanks to all of you. I think this has been productive and I hope we can continue it.
Thank you.